Hi, and welcome to Module 5.7. If we need to get creative in our filter design efforts, there's a fundamental question that we have to answer first. Namely, what is the largest class of realizable filters that we can implement? Now, we know that in order to have a linear time invariant system, we need to have a system described by a linear combination of present and past input and output values scaled by constants. We call this a constant coefficient difference equation. Now, as a CDE is very complicated and cumbersome to manipulate in the raw. So in this module, we will introduce a new tool called the Z-transform that will greatly simplify the task. With the Z-transform, we will arrive at a new characterization for a filter in terms of what we call a rational transfer function, which is simply a ratio of polynomials in a variable Z. Welcome to Module 5.7 of Digital Signal Processing, in which we will talk about realizable filters. In the previous module, we took our first stab at the problem of filter design, taking a very intuitive approach, and we quickly realized that there are some drawbacks to the intuitive methods in the sense that we cannot control certain important parameters, such as the maximum error in the passband, for instance. Before we study more sophisticated methods that will give us full control on the design parameters, we need to better describe the type of filters that we can actually implement in practice. We will find out that the most general type of linear time invariant filter is described by a constant coefficient difference equation. And in order to analyze these equations, we need a new mathematical tool that goes under the name of Z-transform. With the Z-transform, it will be very easy to derive system transfer functions, and from the system transfer function, we will know whether a system is stable or not. We have seen in the previous module that ideal filters cannot be implemented in practice, and so the natural question is, what is the most general, realizable LTI transformation? So we know that linearity implies that we only use sums and multiplications, time invariance implies that we only use multiplications by constants, and realizability implies that we only use a finite number of past and future samples. We've seen this chart before, and these are the three ingredients that make up a linear time invariant system. Under this hypothesis, we can always express the input-output relationship of a linear time invariant system as a linear combination of output samples equal a linear combination of input samples. This system in this equation uses capital M input and capital N output samples. These are the limits of the summations. And the question is, given this relationship, how do we compute the frequency response of the system implemented by this equation? One way to do it, we've seen it in the past, is try to compute the impulse response explicitly and then take the Fourier transform. But for complex systems, this would become quickly unwieldy. So we need a new tool, and the new tool goes under the name of Z-transform. The Z-transform is a formal operator that maps a discrete time sequence x of n onto a function of the complex variable z. It is defined as the sum, for n that goes from minus infinity to plus infinity, of x of n times z to the minus n. Think of it as a formal operator, or alternatively as the extension of the DTFT formula to the whole complex plane. It's very easy to see that the Z-transform computed for z equal to e to the j omega is actually the DTFT. This is a relationship that will reappear again if you have the Z-transform and you compute the Z-transform along the unit circle, which is the locus on the complex plane for which z is equal to e to the j omega, then you have the discrete time Fourier transform. In this class, we will consider the Z-transform mainly as a formal operator, so we will not delve very deep into its mathematical subtleties. But there are two key properties that are absolutely essential to what follows. The first one is linearity. So if you take the Z-transform of a linear combination of two sequences, what you get is a linear combination of Z-transforms. And the second property is the time shift property. If you take the Z-transform of a time-delayed sequence, for instance, in this case x of small n minus big N, the Z-transform is the Z-transform of the original sequence multiplied by z to the minus big N. With these two properties, we can take the Z-transform of a constant coefficient difference equation. So we take Z-transform left and right in this CCDE here, and by exploiting the linearity and the time shift property, what we get is an input-output relationship like so. The z-transform of the output is equal to the z-transform of the input times a function h of z, and this function is defined as follows. It is a ratio of two polynomials in z to the minus 1, where the coefficients of the polynomials are the coefficients that appear in the CCD. In particular, in the case of the numerator, you have the coefficients bk that are the coefficients away the input samples in the CCD, whereas for the denominator, you have the coefficients ak that weigh the output samples in the CCD. Now, if you set z equal to e to the j omega, h of z becomes h of e to the j omega, and you have the frequency response of the system defined by the CCDE. Well, the reason is because, of course, the whole equation becomes like so, and you recognize this as the equation that relates input and output in a filtering operation. So H is indeed a filter, and its frequency response is easily computed via the z-transform. It should be clear now why we use the notation x of e to the j omega, although we hadn't defined the z-transform in the beginning of the class, but now this notation should make a lot more sense. Another thing that should make more sense now is the notation that we use in Module 2 for the delay operator. Indeed, the transfer function of a delay by one system is z to the minus 1. To appreciate the power of the z-transform formalism, let's revisit the leaky integrator and derive its frequency response in a few easy steps. So from the CCD of the leaky integrator, which we remember very well, it's very easy to derive the z-transform. We take z-transforms left and right, then we rearrange terms, and we find out that the transfer function of the system, h of z, is simply 1 minus lambda divided by 1 minus lambda z to the minus 1. One remaining question that we have to answer before we start using the z-transform with reckless abandon is, when does the z-transform exist? For the z-transform, existence is equivalent to convergence of the power series that defines it. And so we will define, for each case, a region of convergence that determines the points on the complex plane for which the z-transform exists. One property to remember is that because the z-transform is a power series, when it converges absolutely. So that means that the convergence of the z-transform depends only on the magnitude of z and not its phase. Let's look at three different cases. The first case is the simplest. When we have a finite support sequence, the z-transform is the sum of a finite number of terms, so convergence is not a problem. In other cases, the region of convergence of the z-transform has circular symmetry, in the sense that, because of the absolute convergence, if the z-transform converges in one point, it will converge for all points in the plane with the same magnitude. Finally, the region of convergence for causal sequences extends from a circle to infinity. So suppose that we have determined that the region of convergence includes this circle. Well, if the sequence originating the z-transform is causal, we know that the region of convergence will extend outwards from this circle. And we will see later ways to determine the smallest circle that defines the region of convergence. Well, this is just a better picture of what I just drew. Given an LTI system, the transfer function is a ratio of polynomials, as we have seen, and that's why it's also called a rational transfer function. So the rational transfer function has a polynomial of degree capital M minus 1 at the numerator and a polynomial of degree capital N minus 1 at the denominator. So we can factor it as the product at the numerator of capital M minus 1 first order terms, and at the denominator, the product of capital N minus 1 first order terms as well. The roots of the first order terms in the numerator are called the zeros of the transfer function because they send the transfer function to 0. On the other hand, the roots of the denominator, they're called the poles of the transfer function, and those are really the trouble spots for the region of convergence because they send the denominator to 0. So, to resume the situation about the region of convergence of a rational transfer function, we know that the region of convergence extends outwards for a causal system, and we know that the region of convergence cannot include any pole. So if we put this together, we can say that the region of convergence extends outwards from a circle that touches the pole with the largest magnitude. So here is an example of a pole zero plot where we represent with x's the poles and with dots the zeros of the function. And if we try to draw the region of convergence, well, of course the region of convergence cannot include this guy and cannot include these guys either. The magnitude of these two poles is the same, and so these are really the largest magnitude poles on the plane, and the region of convergence will extend outwards starting from these poles. The zeros do not affect the region of convergence of the transfer function. Now here is a very handy stability criterion that we can apply once we know the transfer function of the system. Remember from the stability theorem in module 5.3, we said that the necessary and sufficient condition for bibostability is that the impulse response is absolutely summable. Now remember, the transfer function is the z-transform of the impulse response. And because of the absolute convergence property of the z-transform, when the z-transform exists for z equal to 1 in magnitude, then it means that the z-transform converges absolutely, which means that the impulse response is absolutely summable, and vice versa. So in conclusion, we can say that a system is stable if and only if the region of convergence includes the unit circle. So for instance, here we can see that all the poles of the transfer function are inside the unit circle. Therefore, the region of convergence will extend outwards, including the unit circle, and the system is stable. Vice versa, here we have a pole that is outside of the unit circle, here, and therefore the region of convergence will not include the unit circle, and this will be an unstable system. Finally, let's look at a cute little trick that will allow us to estimate the frequency response of a system from its pole zero plot. This is called the circumstant method, and you will understand why in a second. The idea is to think of the magnitude of the z-transform like a rubber sheet that is spread over the complex plane. This sheet is glued to the ground where the zeros of the transfer function are, and the poles are like poles that push this rubber sheet up. And the frequency response in magnitude is the profile of the sheet around the unit circle. So let's have a look. Imagine a simple pole zero plot like so, where you have two zeros and two poles. The complex poles are complex conjugate, as is the case for real-valued systems. Let's plot the complex plane in a 3D perspective, where on the vertical axis we will put the magnitude of the z-transform. So we put the zeros and the poles down, and we can indicate the uplifting action of the poles with deltas like so. Next, we drape our rubber sheet on top of the plane, and we put it at height of 1 to start with, and then we start gluing it to the complex plane where the zeros are. So the first one is here, and so it sticks the rubber sheet down there, and the next one is on the unit circle, and it will put the rubber sheets down there as well. Now we consider the poles one at a time, and so the first pole will start pushing up the rubber sheet. Actually, this thing in theory goes to infinity, but we stop there just to give the idea. And the second pole will do exactly the same. And this is really the shape of the rubber sheet once we've considered all four components on the complex plane. We can turn it around to have a better look at how it unfolds. So now the idea is that the Fourier transform is the value of the z-transform around the unit circle, which means it's the level curve computed around the unit circle on the rubber sheet. And if we plot that, it will look like this. In other words, the level curve will intuitively dip down when it passes near 0 and will be pushed up when it passes near a pole. This 0 is actually on the unit circle, so the level curve will touch the unit circle there. We can turn it around a little bit to see it better. As a final step, we're going to follow the angle from minus pi all the way up to pi and plot the corresponding value of the level curve to obtain an estimate of the frequency response. Well, clearly this is something that you can do roughly in your head without having to draw the 3D picture, but it gives you an idea how to interpret a pole zero plot in order to obtain information on the frequency response of the system.